Hello, everyone. My name is Joy. I am with the cryptography team at Miston Labs. We're the team behind the Sui network. And for those of you who don't know, I'm here to present about the next frontier in authentication with privacy and ZK. It is a new line of research that we've been working on, and we haven't shared it anywhere else. I'm really excited to, tell you guys about it first. Um, and yeah, we'll start by the talking about the authentications in blockchain. We went through a lot of stages of how authentication works. And first of all, we have a wallet, and you provide a single private key, and you present a signature, and the transaction will happen. And soon after that, we realized that's not enough for a lot of the scenarios that we wanted. We've came to a stage of multi-sig, which is supported in majority of the blockchain these days. And you can somewhat define authentication policies with some semantics, mostly with weights and threshold, and you can specify a sort of a structure to how people design a wallet that are more modern and with more flexibility. Some of the downsides is the policies usually is not will be fully reviewed on chain. For example, using a multi-sig, you'll end up seeing who will eventually be the signers, and you also cannot update the structure of a wallet policy very easily. Usually, people will migrate it to new multi-sig, for example. And then there's another whole category of the MPC wallets that a lot of you here are very familiar with, and where you essentially define the authentication policies off chain. It's fully private, and it actually looks exactly the same as a single key wallet on chain, and you just do everything, the signing part off chain and keeping the policy itself flexible, fully private, and also updatable. The downside here is the policy itself are actually not enforced on chain. You usually have authentic policy engine running somewhere else, and you're sort of trusting that deployment is being authenticated correctly. So the question that we ask here is, can we do better than this? In particular, we're looking for authenticator that is very expressive in the policies. Doesn't need to be key specific. What I mean by expressive, it could also support wallets such as like Google login, for example, or your driver's license age is above 21-year-old. And secondly, we want ideal property here is we want the policies that are to be enforced on chain, but they're not revealed on chain. So the policy themselves are hiding. And most importantly, we also want to achieve this oblivious updatability. What I mean by that is that on chain, you should not be able to tell if a policy has been updated for a particular address when they're transacting. So that's sort of the goal we're trying to achieve here, and the most intuitive construction here, as I sort of revealed here, is about using zero knowledge proofs. Let's say a very strawman construction here. We'll start with a policy defined in a zero knowledge circuit, and you can embed anything you want into such circuit. And usually speaking, let's assume that there is a trusted setup that, let's say, a bank can run to generate the proving key and the verifying key. And let's say the bank is only for people who are above 21-year-old, and we somehow need to prove that every time we're doing a transaction. So what's on chain is actually quite simple. The user address can be fixated on the verifying key itself, and the user, all I need to do is to use its private input to prove that the user actually satisfies such policy. And to pin it to the address, the hash of the transaction or have you can be the public input for this transaction. So on the blockchain, the verification is very simple. All you need to do is to make sure that the proof is indeed consistent with the verifying key and also with the transaction itself. And you can also check that the address is indeed derived from the verifying key itself. But when there's a policy update, there is a problem here when you wanted to generate when you want to define a new policy, which is embedded in the zero knowledge circuit. Usually speaking, you need to run a trusted setup again and update the proving key and the verifying key. So now we have a problem here because the user address now will essentially change, and that's not ideal because your address should not change and the user wallet should ideally stay the same. So the next questions here is that can the policy be updated without changing the verifying key? So in some sense, we want to have a circuits being updated without changing the verifying key, which is pinned on chain. So we actually find this very surprising property of Groth16. I think a lot of you guys here might be familiar with this proving system. And a property that we find is actually the verifying key itself can hide the underlying circuit. What I mean by that is that for two different circuits that has generated two different proving keys can actually be pinned with the same verifying key. I wouldn't go into details on the math here for the sake of time, but the idea is that we are able to change the verifying key and the proving key a little bit such that we can achieve this property. So now the construction now becomes this obliviously updatable ZK authenticator where the policies can stay private as part of the zero knowledge circuit, and is also updatable obliviously by updating the proving key itself without changing the on-chain address. So we first start off with like a very naive construction where we define a circuit and we define this policy predicate as a private input to the circuit. There's an issue here where the trusted setup now is actually very expensive when the policy updated. So once we during the setup, so the specific constructions we have here is using this recursive Nizic proofs. The idea here is that we actually separate the proof into two parts, where the inner proof actually corresponds to the policy policy predicates themselves, and the outer proof is essentially proving about the knowledge of the valid proof to the policy predicate and a signature over the inner verifying key. So the idea, the reason why we come to this construction is that in this way, the verifier doesn't really need to know about the inner proof itself or anything updates that happens there, and it only needs to be convinced that the outer proof indeed knows about the proof inside the inner proof and also a signature over the inner verifying key. So to sort of expand on this construction, here are some more, detailed like a protocol construction. As I mentioned earlier, there's the inner zero knowledge proof, and there's also like an outer zero knowledge proof. And the outer zero knowledge proof essentially proves the relations of the knowledge of the proof itself and the signatures. So what happens here is that the issuer essentially needs to run one setup once for all by generating the outer proving key and then an outer verifying key. And at the same time, it also generates signing key pair, SK and BK here. And every time when a user is, a user here would essentially generate per user setup that the issuer essentially need to generate a proving key and a verifying key for the policy itself, and the user address is pinned to this verifying key. And for the user, it essentially will have the proving key and the verifying key and the signature that is required for you to sign transactions. So what happens when the user is signing a transaction? All you need to do is to generate the inner proof with the inner proving key and whatever private input you have to this policy circuit. And then, in addition, you also need to generate the outer proof just to show that you do have the knowledge of this updates of the policy. So, and when you need to do a policy update, all the issuer essentially needs to do is to generate a new pair of the inner proving key and the inner verifying key, and then assign the inner verifying key prime with a new signature. So just to put everything together, we have a policy defined as in a zero knowledge circuit, and we also have a trusted setup run to generate the proving key and the verifying key. And then when the issuer really needs to do a to do a policy update, it essentially preserves the trapdoor to produce a new proving key and a new verifying key. But as we mentioned before, the verifying key actually stays the same without any updates. So only when you're generating the proof, all you need to do is to use a new proving key. So what happens on chain is that you essentially verify the proof is consistent with the transaction itself, and you also verify that the signature is consistent with the signing verifying key. And of course, you also need to check the user address is also consistent to this verifying key you define. So that's essentially the constructions that we have, and to reiterate, it achieves two main properties here. One is that we hide the policies for the transaction in a zero knowledge circuit. And at the same time, we also can update such policy with the issuer can update such policies and perform so that the user, essentially the transaction itself, just need to show that it knows this update of the policy. So so some of the interesting application here that this ZK authenticator enables is that it can actually specify any policy semantics as long as they can be expressed in a circuit. This is really powerful, and earlier last year we implemented like a ZK login in Sui, which is a way to enable people to use Google or any Web2 account to produce to transact on the blockchain. And when you have such ZK authenticator, we can actually bring all these attributes, the ZK attributes, into the authenticator themselves. And in addition, as mentioned earlier, where the policies are actually hiding inside the circuit, so you can actually a lot of the more policy private focused applications can use blockchain as a result. And also, in addition to that, the policies can be dynamically updated without any blockchain footprint. And you can imagine there are places like the banks or people who actually are sensitive to revealing all of these on-chain will be interested in such protocol. And currently we have this more of a research project, but the goal is we can eventually bring it to our blockchain so that people can use this as one of the authentication mechanism. Cool. Thank you. That's all from the presentation.
We have 5 minutes of questions. If anyone has questions, please raise their hands.
So if I hear that correctly, you're saying how can we bring this to other blockchains?
Yeah.
This is so far as a protocol change, and I would imagine well, if you this is like a new authenticator in addition to, let's say, EDDSA or multisig or zk login. Just like how zk login works, we need to enable it by the blockchain. One way I can see this being enabled for other blockchains is having a private smart contract that can implement similar logics. So you using account abstraction. But yeah, I don't know too much about the mechanisms. Yeah. What do you mean by larger? Like more detailed ones? Yeah, that's a good question. I actually it could update to any policy if you want. I guess the only barrier here is to like for efficiencies. Right now we only benchmarked with like a very simple like multi-sig, and the performance seems okay. But yeah, we haven't been testing it. But yeah, to your point, whenever you update a policy, it doesn't matter how big the circuit is. You can always run a setup and change it. Not in the contract. In my particular setup, the verifying key is part of the what the user needs to keep track of. So let's say your on-chain address is derived of this verifying key. And the idea here is that when you update the circuit, you can actually keep the verifying key unchanged and only update the proving key.
We have a question there.
Oh. Hi, thank you for your talk. So, if I understood it correctly, the outer circuit is taking the inner circuit's VK as an input. So, I just wanted to know how we're using the indistinguishability property of graph 16 VKs, since the VK is a private input anyway.
You mean the private input to the outer circuit?
Yes, a private. Yeah, I understood it as the VK of the inner circuit would be a private input to the outer circuit. Maybe I misunderstood that.
The outer circuit only needs to have needs to know the relations of the signature over the inner circuit. So inner circuit is not like a private input, but it's more of verifying the signature of the knowledge of the update. Not sure if I makes sense, but we can talk.
Thank you. Yeah.
We can take one more question. Any last questions?
Okay, round of applause for Joy.
Thank you.